Chapter 18c, Question 1. Find the coordinates of the stationary points of each of the following functions. So the first function being f of x defined as x squared minus 6x plus 3. Firstly, what we need to notice is what order is this function, and if we're looking at it, we can see it's of order 2 because it's a quadratic. There's a square there. Now the question itself is asking to find the stationary points of each of the following functions. So if we were to graph this function f of x, what we'd find is that the function itself, it's going to look something like this. So it's important to remember you've always got your graphics calculators on you for this topic. Now if this was say that's f of x, the stationary point we're looking for is here. Now if we were to take the derivative of this function, what we'd find is that our derivative would look something like this, because on the left hand side of the stationary point we've got a negative gradient, and on the right hand side of the stationary point we've got a positive gradient. And remember, the stationary point is always going to be the x-intercept of the derivative function, so f dash of x, like so. So pushing onward from that, what we can deduce is that the derivative is going to give away the location of the stationary points. Cool. So when f dash of x equals 0, the x location denotes the stationary points for f of x. So simply, 1, find the derivative. Second, find when the derivative is equal to 0. Record the values of x. And then finally, substitute those values of x back into f of x. Thus, you deduce the stationary point, so the locations of the stationary points. So for the function b here, y equals x cubed minus 4x squared minus 3x plus 20 for x is greater than 0. Simply looking at this, what we can see is that we've got an order 3 function. So when we take the derivative of this function, we'll get a second order function, which then implies that provided the roots are real and they are above x equals 0, we're going to see at least 2 roots. Or I should say, we're not going to see more than 2 roots. There's going to be 2 stationary points. Alright, so going down, for question 4, the curve with the equation y equals ax squared plus bx has a gradient of 3 at point 2, minus 2. Find the values of a and b, and then find the coordinates of the turning point. So again, similar question, just phrased in a mildly confusing manner. Think about the graph that we're going to be observing. So instantly we see that there's a gradient of 3 at point 2, minus 2. So what we're going to find is if we go to 2, minus 2, go across 2 down to minus 2, we're going to see a gradient of 3. Alright, so second piece of information is look at y equals ax squared plus bx. What that implies is that we're going to see a parabola or a second order function of some sort. So just guessing what it might look like, I'm going to assume that it might look something like that. Again, we don't know if it's exactly going to be that, but this is just a estimation of what it could look like. So to solve this particular one, we need to find the values of a and b. So instantly seeing the y equals ax squared plus bx has a gradient of 3 at point 2 and negative 2. Instantly what's happened is the point here, the function itself lies on this point. So by subbing in the values in this, so x equals 2 and y equals negative 2, oops, and we'll say for x and y equals 2 and negative 2, then what we're going to get is y, not y, negative 2 equals a2 squared plus bx. So this is the first of two equations we're going to generate. The next one we're going to do is we're going to take the derivative of this function, because we know that the gradient of the function, the gradient at 2 and minus 2 is equal to 3. So if we take the derivative of our y equals ax squared plus bx, then we can form a completely different equation. So we can go y equals ax squared plus bx, and therefore our derivative, dy over dx, is going to be 2ax plus b. Then I'm going to say let dy over dx equal 3, because that's our gradient at this point. And then I'm going to say let x equal 2, because we've got this 2 over here. So the gradient is equal to 3 when x is equal to 2. Therefore, we can construct our second equation. So we're going to go 3 equals 2a2 plus b. And now what we have are two equations and two unknowns. So it's simply a case of solving, that should be a 2. It's simply a case of solving these two unknowns using simultaneous equations, either using the elimination method or the substitution method. Now for b, find the coordinates of the turning point. Again, all we're looking for is, let's go green, all we're looking for is that point here. So if we take the derivative of the function, what we'll find is it might look something like that. And if the turning point here is x and f of x, it's simply a matter of, well, that point there, the x-intercept will refer to x and 0. So simply look for when the derivative of the function is equal to 0, record the value of x, then substitute it back into your original function. So y equals ax squared plus bx, where you know the values of a and b. And that would be how you satisfy this question. Going down, we've got question 9. The curve with equation y equals ax cubed plus bx squared plus cx plus d has a gradient of negative 3 at 0 and 7.5, and a turning point at 3 and 6. Find a, b, and c. So again, it looks like we don't have enough information here, but we in fact do. If we draw a graph, again, it's not going to be accurate because we don't know the values, but it's more of an interpretation of what could be. So notice the order of this function is third order. And because it's third order, we're going to expect something like that. Now, what it tells us is that at 0 and 7.5, 0 and 7.5, we're going to see a gradient of minus 3, so draw a tangent there, and this would have m equals minus 3, and this would be at 0 and 7.5. Now, second part is we have a turning point at 3 and 6. So what we can see is I've drawn the graph upside down, but imagine that that point is 3 and 6. Of course it's not, because it should be above the x-axis, but just suppose it was, and I'll do it in a different color as well. That's better. Suppose it's 3 and 6, then this turning point here tells us that if we took the derivative, this would be 3 and 0. So to solve this particular question, what you need to do is firstly build two equations where you're using the gradient point and the turning point here, because these tell you that these 2 points lie on the function y, and then take the derivative of y and the turning point itself, so 3 and 6 will lie on the function, but not 3 at 6, but rather 3 and 0. So using those functions there, you should be able to construct an equation y equals ax cubed plus bx squared plus cx plus d simply by putting all those together. So getting it started, we're going to have y equals ax cubed plus bx squared plus cx plus d. Then we're going to say let, let x and y equal 3 and 6. So our first equation is going to look like 6, 3 cubed plus b, 3 squared plus c, 3 plus d. So this is equation 1. Equation 2 is going to be y equals ax cubed plus bx squared. And next one is let xy equal the location of the stationary point. So, oh no, we've already done the turning point. We'll go for the second one, so where the gradient's at 0 and 7.5. Like so. So what we can see is that 7.5 is going to be equal to a times 0 cubed, b times 0 squared, c times 0 plus d. So this is going to be your second equation. And then finally, we're going to take the derivative of y, and we'll just jump straight into it. We'll go dx over dy. It's going to be 3ax squared plus 2bx plus c, and the d is gone. Then we simply say let xy equal 0, 0, because oops, not quite. We're going to say 3, 0, because this guy here, it says it's a turning point, so therefore the x location in the derivative, when x is 3, y will be, or dy over dx will be 0. So piecing that together, we're going to get 0 equals 3 a 3 squared plus 2b 3 plus c. This will be equation 3, and I know I said that we're only going to get 3 equations, but in fact we're going to construct 4 equations. The final one will be dy over dx equals 3ax squared plus 2bx plus c, and then we're going to go for that stationary point, or the turning point I should say, so this guy here, which is a stationary point. So that's going to be, sorry, not the stationary point, the gradient, so this guy and this information here. So we're going to say that let dy over dx equal -3, and also we're going to let x equal, going up, when the gradient is equal to -3, we're going to see x equals 0. So putting it all together, my black pen, we're going to go -3 equals 3a 0 squared plus 2b 0 plus c, and this will be equation 4. Now, looking at equations 2 and equations 4, they're actually really good equations because they sort of give away the values of d and c. So in effect, you're only going to have although it looks like you've got a model of 4 equations and 4 unknowns, in reality, when you start piecing it all together, you'll find that the question's really a case of 2 unknowns with a count of 2 equations. So simply solving via substitution or elimination, you'll be able to do this question here. So that should be enough information to get you started on how to do question 9, question 4, and all of question 1.